Life on Earth flourishes thanks to the thin bubble, the atmosphere that surrounds it. Outside this bubble is space, a hostile environment constantly bombarded by searing radiation, subjected to extremes of temperature, an environment that apparently will not support life. For 10 months, this environment is home for Eureka, the European Retrievable Carrier, an unmanned platform that's taking scientific payloads into near-Earth orbit. Eureka carries 3 experiments that will make future long-term space travel safer and more reliable. Only through long-term exposure in space, the real operating environment, can scientists assess the performance of equipment that, in the future, will support experiments on board other unmanned space platforms. Also on the first Eureka mission is an experiment designed to capture microparticles, small pieces of matter trapped in orbit by the Earth's gravity. Matter that might just be of interest to scientists here on Earth. Space is littered with all kinds of particles. The debris from solid rocket boosters, flakes of paint from the various spacecraft, cometary dust, meteoroids. The time-band capture experiment on board Eureka is designed to collect these microscopic particles. Once Eureka is retrieved and returned to Earth, the impact holes made by the particles can be examined and identified. There's every chance that some of these particles might be organic. The experiment is simple in principle. Pointing out towards deep space, the flat surface will capture a wide variety of particles. As the particles travel towards the satellite at speeds up to 10 kilometers per second, they impact through a thin layer of foil and splatter onto the substrate behind, leaving chemical traces on both the foil and the substrate. The layer of foil moves very slowly during the course of the mission, giving the analysis team some indication of when each impact occurred. Here at the Space Sciences Department at the University of Kent, painstaking work is underway on collection instruments from earlier missions. As each small impact hole is found and then analysed, it's become clear that there may be organic particles in space that we know very little about. The capture of a single particle on the Eureka mission may solve mysteries that have intrigued scientists for hundreds of years. All space vehicles demand reliable and efficient power supplies. Solar arrays are the source of that power. Oriented towards the sun, they trap sunlight and convert it into electricity. Frail and too delicate here on Earth, they have so far proven to be adequate in space. As satellites get larger, so their demands for power increase. Eureka itself is powered by these conventional arrays. But advanced solar cells are undergoing rigorous in-space testing, cells that use new materials in an attempt to produce significantly more power for their weight.
Flights now already involve several kilowatts of electrical power. This means having a solar array, or solar panels, of enormous dimensions of several tens of square meters. By increasing the efficiency of the solar cells, it is possible to reduce the dimensions of these solar arrays, with a resulting saving in fuel for putting the satellite into orbit, and preventing the drag effects which can occur when satellites fly in low orbits.
In a carefully controlled laboratory environment, each of the experimental cells is vapor-coated with a thin layer of gallium arsenide. It's a substance that has already proved to have significant advantages over conventional silicon-based cells currently used in space.
This material has shown various advantages compared with current solar cells made from silicon. Gallium arsenide solar cells, in actual fact, are far more effective at converting solar light into electrical energy than our current silicon solar cells. In addition, these solar cells have a greater resistance to radiation. Therefore, their electrical performance degrades less during the course of their life through exposure to the space environment. It is these advantages which are of interest in evaluating the characteristics and properties of these cells in situ.
Before they're subjected to the rigors of the space environment, each cell is checked and calibrated. Vital to the performance of the cells is a series of connectors that link the cells together into a single solar array. In space, many materials in current use degrade because of the intense radiation, reducing the overall efficiency of the power supply. On Eureka, new materials for these connectors are being tested for the first time.
In this orbit, the solar cells, the panels, are subjected to a considerable range of thermal cycles. They are getting on for 6,000 thermal cycles due to eclipses during the course of the mission. This means that the solar cells find themselves in the sun, in the dark, in the sun, in the dark every 90 minutes, which consequently causes a whole range of stresses on the mechanical structures. This involves another effect, which I mentioned earlier, namely that of atomic oxygen erosion. This atomic oxygen causes corrosion of the metal parts, certain metals in particular, used in the manufacture of the solar cells. For example, it causes the corrosion of the interconnectors which link the cells to one another, which usually are made from silver. We'll be experimenting with a series of interconnectors made from new materials: molybdenum, gold-plated molybdenum, silver-plated molybdenum, gold-plated silver, because molybdenum and gold are materials which are resistant to erosion from atomic oxygen.
Earthbound testing cannot simulate the rigors of the space environment. It's only through retrievable flights, such as Eureka, that this technology can be brought to the levels of reliability and safety necessary for long-term manned missions. Safety and reliability are also crucial in space communications. All orbiting spacecraft need to keep in constant touch with ground stations to receive commands and to download data. Because of the Earth's curvature, a spacecraft in low Earth orbit needs several ground stations to keep in touch with ground control. In higher orbit, the number drops considerably. But what ground stations cannot offer is the facility for spacecraft to communicate with each other via a geostationary data relay station. 3 or 4 of these relay stations will ensure constant communications without the need for ground contact. On board Eureka is test communications equipment that will assess the viability and reliability of communicating on a long space mission using another ESA satellite, Olympus, as the relay station. For over 30 years, our exploration of space has come about through the use of chemical propellants and rockets. These rocket engines are without doubt effective, but they do have limitations. They're bulky and the fuel they consume is heavy. The result is a reduction in the size of scientific and commercial payloads that can be lifted into orbit. Because of their enormous thrust, conventional rockets will continue to be used to defeat the effects of gravity. But for in-space maneuvers, a new generation of thruster is being tested on board Eureka. This is an ion thruster. At the University of Gießen in Germany, the large yellow vacuum chamber simulates space.
Okay.
Underneath, a computer control system monitors the performance of a thruster under test. Before testing in space, hundreds of hours of work are carried out in this facility to ensure that the unit is reliable and safe, and that it won't destabilize other experiments on Eureka. In the thruster itself, a gas is ionized and the positive ions accelerated by an electric field. The resulting blue ion beam or exhaust is neutralized to avoid charging the spacecraft. The resulting velocities are about 10 times greater than chemical thrusters currently used. This prototype thruster will be operated for around 2,000 hours at varying levels of thrust. Eureka provides an ideal platform to test new technologies in space, technologies to power and propel future spacecraft, and allow them to communicate successfully with other space systems.